arrive in a couple minutes. presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you onto the stream here today. I want to apologize foremost, because I was intending to start at 1, well, Central Time, but we had a couple of little disruptions here or there and had to get things going a little later. So hopefully that is okay with everybody. So, anyways, before we get into everything, I thought I'll just get into my usual things I need to announce. So the first thing is, of course, if you're enjoying what you're seeing, make sure you tell your friends to come on out and learn some fun computer science stuff that will definitely help you better understand computation and how you might use it. Either way, we're really big on trying to figure out why questions. So today we're going to be mostly focusing in on the dreaded M word, the mayonnaise or mustard, whatever you might call it. I don't know what the word is, but the point I'm getting at is that we're going to be focusing in on kind of the mathematical side, but there, I said it, oh no, of how we might analyze an algorithm, but in particular we're going to focus on the big O and its relatives, big O, big omega, big theta, and little o. We're going to focus in on those today in relation to what I would call small functions. These are functions for which the output of them aren't very high. And I want to show you that there's an interesting edge case that happens depending on how you define what we call a complexity or growth function. So you're going to find that depending on your definition of this, it'll actually, as we're going to see at the end of this lesson, we're going to see that whether an algorithm actually exists that meets that or not. So we're going to be kind of building up to that, but I mostly want to use this as an exercise to talk about and give examples for proving claims involving asymptotic notation. So whether it be I want to show something is satisfying that property or doesn't satisfy that property, that we're going to focus on that today for the most part. So this discussion about the existence or non-existence of a certain kind of algorithm with a certain running time, that's just a thing that's got to kind of weave itself in and out of this discussion that I'm hoping that we can engage in together. Okay, everybody? I always like to do it where we're doing stuff here together. So before we get into today's lecture, I mostly wanted to get into just a couple other things. So first, I am working on a couple of other projects. So I have a few other things going on, whether it be research. I'm currently working on a collaboration with a couple other researchers, at least, from different universities. So I'm hoping I can get more time to focus in on that. It's pretty interesting stuff. It's an interesting problem, and at some point I will give some more discussion of this for those, especially those that are, say, supporting this work on Patreon. So patreon.com/pagewizard. That is the way you can support this channel or the work that I'm doing right now here. I am working on some ongoing projects to make learning much easier to do together with all these lessons. So I have an ongoing project right now. I'm actually working on the website that I'm hoping that we can facilitate the educational materials much easier. And say if you don't want to use Patreon as a supporter, I'm hoping that I'll be able to provide a more direct means for doing that online. So that is something that I am working on. So just give that hopefully I'm hoping that we'll have something that will better facilitate self-learning and be able to do stuff together like this. So other than that, one other thing I want to point out is that I am testing out with some improved lighting. You may or may not be able to notice, at least in the present shot, that the lighting has been improved upon. So I have more lighting, especially on that side of the scene. So let me know what you think of that. So leave me a comment or tell me in the chat what you think about it when we get there. So usually that side tends to be a bit dimmer than this side. So I'm hoping that I've kind of remedied this issue for the most part. Other than that, I am working on another another project that is involving academic freedom. So I will be working on that as well. I'm hoping to produce a video that's going to go along with some of the work I'm doing on that. This is to raise awareness of a serious issue that is going on in computer science departments across Canada. So I'm hoping that you'll be able to share this message along when we get there, okay? Either way, I want to bring this to your attention because it's very important that the general public is aware of changes that are happening within the university system in Canada. So, anyways, let me know what you think, and of course, let me know in the chat how are you doing. Let me know also about the audio levels, as per usual. What I'm going to do is I'm going to get started here, and we're going to be defining some things. So a lot of this is going to feel like stuff I've covered before for Big O Bootcamp at first, but it's going to start deviating quite heavily. So just keep in mind, and remember that the end goal here is to understand how we can prove claims using asymptotic notation, and it's the asymptotic notation that we use to describe running times for algorithms, but the asymptotic notation itself is in relation to functions. So it's a statement about a function. So we're going to talk now about this, okay? So if you have any questions, just put them in the chat. I have them right in front of me over here. And of course, feel free to join us on YouTube, on other platforms as well, like Twitch. Make sure you come and say hi. We have ourselves a good time on over here. So other than that, hope you sit down in and hopefully you'll learn something new. If not, come join the fun. So I know I always enjoy this. So anyways, let's get started. So what we're going to do is we're going to focus in on the measuring of algorithmic running times. Now, there's several ways you could define a function that would represent this. I'm going to be using, and I must stress that this is a very convenient definition that makes it easier to work with in more broader settings. So we're going to come back to this definition and revisit it towards the end of the lesson that we go through eventually. So the first thing I want us to do is we're going to define what we're going to call a complexity function. So some people call this a growth function. But the real thing about the complexity function is that we're trying to use this function to represent the running time or the space usage of an algorithm, the complexity, hence why I've called it a complexity function. I must stress that as we're going to see in today's lesson, I'm going to show you that eventually I'll show you that maybe this definition, like I said, it's very convenient, but it doesn't necessarily give us everything that we might not necessarily need all of this, but it's a very helpful definition that reduce the amount of formulation you require to come up with a useful complexity function for measuring time complexity. So I'll have some discussion about this as we go along. So first, a complexity function is a function f on the size of the input. And you might ask what the size of the input is. That is that we're talking about the input size. If you're not familiar with this concept, whenever I'm trying to solve a problem, I measure out how long the input is in terms of some measurement. In this case, in computer science, we'd normally use bits or any what we would call meaningful encoding scheme. So ternary, for example, is another one, but not unary. Unary is not one of these. But my point is that you can just think of that as just a number, which we will write as f like this as an abbreviation, just to specify what the input of the function is. Now, you might say, Dan, what is this? Why do you mean that this is an abbreviation? It's because it's technically an abuse of notation to both write this, but also expect the following. Because remember, a function looks like this. So if you've never heard of what a function is, I like to visualize it like a machine here, where you have say the name of the function, we'll call it f. So this would be its name. So that's what f means, that's the name of the function. So whenever I refer to the function, that's its name. It takes an input. It may take in multiple inputs, but it takes an input. So in this case, it takes an n. And as output, it gives me what we call f of n. So this is the output from the function. So for each one of the inputs, I get output. Now, you'll notice here that what I've written here is the output of the function. This is, given this input, this function spits out this value, whatever it might be. This is what we call f of n. This over here is an abbreviation of f, so I can specify what the input is. So please just don't confuse these two different things. They'll be used contextually in similar manner, though. So just be aware of that. So we will assume, so this is out of convenience for us. This is a convenient definition for our sake for this lesson. We will assume functions on the domain of positive integers. So that's numbers starting at 1, 1, 2, 3. So you're counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm starting it there, but I must stress that this does not change a whole lot if you just allow it to also have it where it starts off at 0. That is something you're more than welcome to do with this definition. I'm just going to keep it this way for simplicity. But it's convenient sometimes to just start it where the input is allowed to be 0 to non-negative real numbers. So more formally, we would write this as follows. So f, it takes as input a positive integer, which we would denote with the set of all positive integers as so. This blackboard Z, that represents a set of all integers. So that's like all your negative counting numbers, 0, and all the positive ones, as we discussed. The plus here is just to indicate that's positive. Meaning it starts at 1 and goes up. And whenever I put this into my machine f, it spits out a real number. So this is the set of all real numbers. That's what this blackboard R represents. And I'm going to use a little bit of notation just to indicate that it is non-negative, meaning it's 0 and up. It can't be negative. This is very intuitive for the discussion that we're currently having because, one, you can never have a computer program that performs a negative number of operations, correct? So there's no reason to ever consider a negative number here. So just please keep that in mind. So when I'm formulating the functions, I'm going to presume that they have this form. So we're going to see lots of examples of functions here today that will fit this definition, but I must stress that this is a convenient definition for us, as I've already previously stated. Sorry, I'm getting really excited here. The reason why is because I want to talk about functions that have small outputs, meaning that when I put inputs in, it gives me something that's a small number. Okay, that's going to be the main thing I'm going to focus in on here today, but you're going to see plenty of other examples too. Just think of this as kind of a common thread that's going to run through these lessons. So one way we can capture what we call the asymptotic behavior of a complexity function, or the asymptotic growth of a complexity function, or it's what we'd call its order, is to use asymptotic notation. This is how the function behaves for sufficiently large inputs in relation to another function. So there's a lot of different kinds of functions out there that are these complexity functions. So for example, you have what we call the constant functions. So you might think of this like, if I have my function, it gets an input, it spits out 1 every single time, or 2, or 10, or something. It's a constant here. So it's some constant, say d, where d is a constant, and say it's greater than 0. It's just some constant. So for example, if it was f of n is equal to 1, or 2, or 3, these are examples of constant functions for our discussion here. I must stress that our definition allows us actually as well to include a 0 function. So that means that It's a special kind of constant function where you're allowed to have it where it's f of n is equal to 0. So what we're going to focus in on today is we're going to see that there's this edge case that kicks around between these two. And that's what I want to focus in on because there's not a whole lot of discussion out there. If you watch a lot of lectures on Big O and all that stuff, you won't see a whole lot of discussion about this. And I'm going to explain that so by the end of this lecture, you'll understand why. So that's really the fun that's hiding behind this. But there's other functions out there too. For example, there's linear functions. So those are things that take the form that look like this. Like it looks like this, an plus b, where this is a constant, that's a constant. These are both constants. So that's a linear function. There's other functions. There's several other kinds, like there's quadratic. Another one that we'll run into is a logarithmic function. So these take the form of following, like log base 2 of n. This is just you can think of this as an inverse operation of exponentiation. We'll talk more about this as one example here today. I must stress that if you're laying these out in order of their asymptotic order, the logarithmic one would go between these two. But what I want to do is come up with some asymptotic notation so I can lump the functions into different buckets. And depending on how I define this notation for you, they're going to lump into different buckets. We're going to start off with easily one of the most common types of asymptotic notations. And what it does is it organizes buckets by nesting them in successive orders. So for example, you're going to see, as I'm going to prove for you in today's lecture, that for example, the 0 function, this guy is, all the functions that are of this kind are versions of constant functions. But the orders may potentially be different. But the thing is, they're going to nest into each other. Like 0 is going to be inside of this one. This one's going to be inside, constants are going to be inside of this one. And logarithmic functions are going to be inside the linear one. So you're going to see this, how this is going to play out with Big O. But it's going to have a different kind of relation each time I introduce some more context. So this one, in this case, when we start talking about what we're going to call Big O notation, it's about, if you want to think about these functions as the running time of the algorithm, so that I put in like say if I was trying to solve the sorting problem and I have an array, so I have a list of numbers of length n, and I want to sort them, I want a function that represents the running time, and usually it's the upper bound on the running time, the worst case running time. I want to measure how long or how many operations more specifically it takes in the worst case. So for each one of these n's, this would represent, for example, the length of the array. And what it spits out is how many operations have occurred in that case. So that's what the complexity function would represent. So let's talk a little bit about this. So let's first consider Big O notation. So hopefully the setup is clear, everybody. So we're going to talk about different kinds of asymptotic notation. So we're going to talk about Big O. We're going to talk about another one called Big Omega. We're going to talk about Big-Theta. And we're going to also talk about one called little o, which is just a lowercase o. That Big O, there's a capital O, not to be confused with a 0. But we're going to talk about all 4 of these in relation to functions that sort of sit around this camp right here. Because sometimes when you're dealing with functions more broadly as opposed to just ones for running times of algorithms, sometimes there's these weird edge cases that happen around these two classes here. So anyways, is that clear, everybody? Okay. So if clear, let's proceed. So just remember, we're going to be talking about functions. These things we're going to call complexity or growth functions. We're going to be interested in the asymptotic orders of them. That means that which one grows faster or if I want to compare 2 different running times, which one will be more efficient for sufficiently large inputs in certain circumstances. So the way this would get set up, as I've discussed previously in series like my Big O Bootcamp series, which I encourage you to check out if you're curious more about some of that background. Remember, the whole step in this process is that you would identify a type of analysis. Once you have an algorithm, you identify how you want to analyze the algorithm. You formulate what we call a complexity function, and then you derive that by counting operations of the algorithm based on the kind of analysis you're using. Then you try to figure out what the relationship it has with respect to big O, or big omega, or big theta, whichever would be most appropriate for your setting. And I must stress that there isn't just one tethered to a kind of analysis. It just depends on what you're trying to describe. So let's talk about big O, okay? So let's define what big O is. So what we're going to do is we're going to let F and G be complexity functions. So just as a reminder, remember that these are going to be taking in a positive integer, or if you want to be charitable, you can also include 0 in that, so 0 and up. It's going to take in these counting numbers as inputs. They're going to represent, say, the size, if we're talking about algorithmic running times, the size of that input. And then what it's going to do is it spits out a non-negative real number, at least in our definition. So we write F is big O of G if and only if the following is the case. So for those that aren't familiar with this phrase, this if and only if phrase, what it's saying, hi Miss Kitty. So what it's saying is that if I say something like this, like F is big O of G, what it's saying is that whatever follows this is equivalent to me saying that. So if F is big O of G, that means that whatever follows here also has to be true. Likewise, if this is false, that means that F is not big O of G. Okay? So if and only if there exists some positive real constant C. So very often I'll abbreviate this as follows. So very often I'll abbreviate this like this. So C is in the set of all positive real numbers. That's what this says. And a positive integer n0. So these are both constants. I'll make that clear. Let me just write constant right here. Miss Kitty, what are you doing? What are you doing? You're not supposed to be up here, you funny kitty. Come on, my friend. You're gonna go down. Here you go. She'll be back. So, such that for all n greater or equal to n0, it has to be that the following inequality holds. So f of n is less than or equal to c times g of n. So let me break this down a little further, okay, everybody? So what this is saying is that there exist these two constants, c and n0. And it has to be that this inequality right here has to be satisfied for all values that are n0 or greater. So these are on integers, right? So that means that it has to be, for example, if n0 is 1, for example, then it has to be true for 1, 2, 3, 4, 5, 6, 7, and so on. If n0 is, say, 10, then it has to be true for 10, 11, 12, 13, 14, 15. The point is that this is what we would call an existential statement. So it's saying that there exist these two constants such that this property holds. So the game in town is to identify two constants, but you have to prove that they in fact are going to work. That means that for all n greater or equal to n0, this inequality is satisfied. Is that clear, everybody? So let me show you a picture of what I mean by this. So let me show you. So suppose I give you two functions. So here's a linear function, and here's a quadratic function. I'm not going to get too delicate with this. And Miss Kitty, what do you want, Miss Kitty? Oh, Miss Kitty, you're being silly. You silly, behave yourself, okay? I know, she's been a real rascal lately. So suppose I have this quadratic here and this linear function. The details about it aren't terribly important. I encourage you to find just some linear function, some quadratic. It doesn't matter too much for this picture. The point is that this is as I increase the input n, and this is for the output here. So for example, suppose that this is say f, and this is g right here. So the point is that there's going to be some constant multiple of g such that there's going to be a point eventually, n0. Keep in mind, n0 could be that point where they cross each other. Keep in mind, a function may cross multiple times. But the point I'm getting at, the point is that there's going to be some point where this function, this g times some constant multiple, is going to be dominating f. So it's going to dominate f eventually. So for all points after this, because this function will dominate f with this constant multiple, for all values after this. So this is for n0 and later. So keep in mind, n0 could be anywhere along this line on this axis here. So keep in mind, the shape of the function might be a little different. It could be that maybe it beaters up and down a little bit, then starts going up. The point I'm getting at is that there's going to be some point where this happens, such that if I take a constant multiple of g, and keep in mind, you have control, as long as they exist, you have control over c and n0 when you're proving claims like this. So we'll see an example of the sort shortly. So very often when somebody says something like this, the way you would abbreviate or say this is you would say f is big O of g. Sometimes people will say that f is of order g. Keep in mind that you have to be a bit careful when you use big O notation. I'll have more discussion about that when we get to some other asymptotic notations. So, likewise, you can also say that f is in big O of g. So you'll find that I'll very often use the first and the third very often when I'm describing things for you, okay? So, first thing, I use this phrase in right here as opposed to just is. There's actually a literal meaning for why I'm saying that. It's because when you write big O notation like that, it actually represents a set of complexity functions. So what do I mean by that? So big O notation represents a set of complexity. Yes, I know, Miss Key. Yeah, it is a set. Is a set of complexity functions. So very often when somebody says the word is, it literally means is in, okay? So very often you'll see when somebody writes this, they'll say f is in, akin to what I just wrote over here where I had some element that is a part of some set. So in that case, a number is associated with a number set. Here is a function associated with a set of functions. So very often it's written like this. And we're going to see that with big O, it operates as an asymptotic upper bound. Asymptotic simply meaning there's a sufficiently large value of the input in this case. So sufficiently large. asymptotic upper bound. Sufficiently large input such that it's going to be that a constant multiple of this will dominate the function that is in big O of G. So this is actually a set. So big O of G is a set. So for example, like I discussed a moment ago, when I talk about, say, big O of 1, big O of 1 is actually a set of functions. Here's a picture, for example, of what big O of 1 might look like. It could, for example, have the function for which it outputs 1 every single time. It may have another function for which it outputs the number 2 every single time. It may have another function for which the output is always 100. But there's many more that might be in here. We're going to see that because of the fact that because of the direction of this inequality right here, that it's going to be that they're always going to be successfully nesting in each other. When I give you one order of a function, if there's one for which it will dominate it, it sits either in the same set or it's going to be contained in a larger set. Okay? So just as an example of what I'm talking about here, as we're going to see in one of our examples here, we're going to see an example of a linear function. And a function like that, like n or 2n minus 1, these are going to belong to another set called big O of n. Those are versus this one, which is big O of 1. So they're going to be nested in like this by the orders of these functions. So the order, the asymptotic order. I should be a bit more precise. The asymptotic order of that function. So hopefully that's pretty neat. So remember, it represents a set of functions. Another standard way people write f is big O of g is also this way. Using an equal sign like this. However, I must warn you that this is not an equal sign. At least in the way that this means is. So it's actually saying is. It's not literally saying that f is equal to g. Sorry, big O of g. It's saying that f is big O of g. So you might ask, Dan, why would you use this? It's because very often when we study asymptotic notation like this, it's very often handy for simplifying calculations to have it so that you can operate on it like you're manipulating functions in a part of an algebra, but also you would like to be able to state these things by clumping them together by their asymptotic orders, as in using the big O notation. Just a quick example of what I mean by this. So say, for example, I have 2n squared plus 5. Instead of writing 2n squared, one thing that we can prove using the definition is that 2n squared is actually big O of n squared. Likewise, you can also prove that 5, as I discussed over here, is also big O of 1. So all you do is you look at the order, the asymptotic order of the functions in terms of the big O, and you take the one that's the most dominant in this case because there's a constant number of terms. If that wasn't true, you have to be a bit more careful. And I can just say that that's big O of n squared. This very often comes up if you have an algorithm with multiple steps in it. You may want to analyze parts of the algorithm, then add up all the operations. And after you've done that for each one, then you can bring them all together. So that's a very common usage of the big O notation. The point I'm getting at is that you cannot read this back like this. Because remember, this says this is a set of all of at least contains all the quadratic functions, but you're going to lose a lot of information when you write big O of n squared. Because remember, like I said, these functions are inside of buckets, but they nest within each other by their asymptotic order. So for example, something like the function n is big O of n squared too, because it's in a bucket that's in one with a lesser asymptotic order, right? Because it's a linear function, not a quadratic. But you can actually sit down and use this definition to prove that. So you lose that information as soon as you try to expose that out here. You're gonna lose that information. So it doesn't work like an equality. This isn't an equation. What I'm doing is I'm actually doing a shorthand representation of this as big O notation so I can perform very simple calculations. It's meant for simplifying calculations like this. You can be very precise about it, but you have to be careful about this, okay? So anyways, let's chat about this now. So now that I have defined big O notation for you, I think it's important that now we talk about an example. Let's do an example together. So I thought I would pick one of these functions that I have over here on the board. So let's do an example. So let's prove using the definition of big O that 2n minus 1 is big O of n. So let's try proving this together, everybody. So what I was going to suggest is we take that definition that we've written over here, and let's think about it as a game plan. So what was the original game plan? Let's back up over here. So this definition over here had two things you're supposed to find, right? So that's what it says. Remember, it says that f is big O of g if and only if there exists what? There exists what? What does there exist? There exists what? There exists some positive real constant c, a positive integer constant n0, such that for all n greater or equal to n0, that inequality has to be true. So the game plan here is that we need to identify c and n0. And remember, it's a statement about the existence of them. So we have choice over what these are. We have to then, once we pick them, we have to check that this works. A common mistake students make is that they just pick c and n0, which is blindly, and they just test this for a given value of n. That doesn't work. You have to do it. You have to make sure that this inequality works for all n greater or equal to n0. That's the catch. So let's do this together here. So we're going to try proving this using the definition of big O. So remember, the game plan is that we need to find c and n0, and that's what we're going to say at the beginning of our proof together, okay? So we find constants. Constants c, which is a positive real number, and n0, which is a positive integer. Such that for all n greater or equal to n0, what was the inequality again? It's f of n is less or equal to c times g of n, right? So f of n is 2n minus 1. Then we have c times whatever is inside of here, right? So it's c times n. So we have to find the two constants. So one tip I can give, and this isn't the only way of doing this, this is just a suggestion. One way to achieve this is by simply picking one of the constants and then deriving the other constant. That's a very common strategy for proving claims involving big O. I find usually picking c first is helpful. But it's not the only way of doing it. It's just a common way of approaching this. So what I was going to suggest is that we try to pick a c that makes sense for us, okay? So I have an idea. So you'll see that I have on my left-hand side of that inequality, do you see how I have 2n minus 1, but it has something that looks like an n right here, right? It has n times a something minus 1. Can I make this look kind of like that so that it makes it easier for me to pick c? Now, there's several obvious choices once you get this idea in your head. So let me show you what I mean by this. So if I have, say if I have 2n, that's two things in my bucket. There's two n's in my bucket here, right? Now, I have a minus 1. That's a something, right? Now, keep in mind, that's only negative. It's going to make it smaller, but I'm going to be overly generous. I'll come back to it. And I'm just going to say, okay, that's another term that I could write in terms of n, right? I can replace 1 with n, just imagining this in my head. I would make it, instead of not minus 1, I would make it just n, right? So I have three things that I can kind of make look like an n. So I have specifically two n's, and I have something that I could write in terms of n if I wanted to. But on the right-hand side, I would like to be able to match these three things I can write sort of like n with 3 things that are n. But you'll notice that if I have 2 n's on the left-hand side and 2 n's on the right-hand side, they match each other. And whatever's left, if I include an extra n on this side, it most certainly will be larger or matches whatever's on the left-hand side. So we're going to use this bucketing approach to decide on what to use for C. So is any ideas of what we should pick for C? So keep in mind there isn't just one answer here. There isn't just one answer here. So what we're going to do is I'm going to pick, just for the sake of simplicity for us, as I mentioned, we can get a little bit smarter about this, but I'm just going to keep it simple. We're going to pick C is equal to 3. So we're going to start off with 3, and my goal is to figure out what n0 should be. So keep in mind, if we don't necessarily have to find the smallest value for n0, it could be any value for n0. Just the catch is that you can't just guess it. You have to prove that that actually works. So it's usually you have to derive that using an argument. So for example, I can't just say n0 is 10,000 and just leave it at that. I actually have to show you that n0 can be 10,000 and it would work. But I'm going to show you an elegant way of arguing this, just to keep it simple for us because it's our first example. So we're gonna pick C is equal to 3. Then we need to find n0. We need to find n0 so that 2n minus 1 is less than or equal to 3 times n. That's what it means when I put C in, right? So now I have to figure out, just like in my picture I had over here, so now I have 2 linear functions that I'm playing around with, right? I have to figure out where this n0 can be. Now remember, n0 is a positive integer, right? We can't just simply just say, hey, look, I'm just going to make it 0. You can't make it 0 because 0 is not a positive integer. It starts at 1 and goes up. So now I'm going to use my bucketing idea. Observe that 2n minus 1 is less than or equal to 2n plus n. So this is what I was talking about. I'm going to make the minus 1 look like something kind of like n. Now, a mistake I could make is I could make it minus n, but we're going to not do that. We're just going to try to come up with an upper bound on 2n minus 1. So I'm just being very charitable on how I do it. But I want to write it in terms of the function. So in this case, n. So in terms of g. But that's just 3n, right? But my claim is that this actually will work for every n greater or equal to 1. For the following reason. So as you can see, that 2n is less or equal to 2n, right? Like we mentioned with the buckets, right? This is because you can divide both sides of this, and you get 1 is less or equal to 1. So this is true for all n greater or equal to 1. And minus 1 is less than or equal to n for all n greater or equal to 1. Right? So you wonder where I get the 1 from. It's because I've taken what's on the left-hand side, I've compared it term by term with what I've written right here. So I take 2n, I compare it against 2n. I take minus 1, I compare it against n. So that's what I'm doing right now. So what I do is, if I could show that each one of these is less than or equal to the right-hand side, then what I do is I sum over these, and I get what I have right here. Does everybody see that? This is what I'm calling the bucketing approach here for you. So let's talk about this. So now I have a reason why this would be the case. So now I know that this will work for all n is greater or equal to 1, right? So I'm going to choose n0 to be 1. Now I must stress that you could have picked n0s 2, 3, 4, 5, 6, 7, could have been 10,000, but notice that the way my argument works is that it seems like 1 is a very natural thing to argue here, right? It's the largest value among these that I have here. So I choose n0 to be equal to 1. Therefore, now I need to make sure I have a conclusion that invokes the definition of big O. Because remember, I'm just saying that we found the constants. I didn't say why we're doing that yet. So I'm going to invoke the definition of big O to conclude our proof. Therefore, by the definition of big O, 2n minus 1 is big O of n. And we're done. So that box there is just to indicate the end of the proof, everybody. So, are there any questions about that? Are there any questions? Don't be shy. I'm not sure if there's any weird performance issues on your guys' end here. I just want to make sure that we're doing okay. It's been awfully quiet here today. Because I don't see any questions in the chat. I think people are doing generally okay. I know there's some people watching this in a few different places. Okay. Okay, so it appears there aren't any questions. So what I'm going to do next is we're going to do another claim. We're going to prove another thing together. So I'm just going to erase the boards here. So that way we can get to our next example. And this next example only merely exists because of the way we defined the complexity functions. So that's one thing I really want to stress here. Now you might ask, Dan, why did you define it so that the complexity function can be 0? Or can be values that could approach potentially 0? It's because I want to make sure that we are able to account for, if we're counting objects. I must stress that an algorithm is just another mathematical object, by the way. So I can analyze an algorithm just like I can analyze all sorts of different things. So for example, like a network, I can analyze a network, prove properties about that network. I presented this definition for you because you can count all sorts of different kinds of objects. Sometimes the number of objects happens to be 0. So just keep in mind that. And likewise, at the same time, this also keeps it a little rich for you given the fact that we're playing around with real numbers, because it makes it a little bit easier to play around with if you're allowed to permit the function to be 0. So for example, if you had trig functions. All right, I'm having a day here today. I'm sort of working on an ankle here. So for example, if you're working with a trigonometric function and you shifted it by 1 so it's non-negative, sometimes it's going to hit 0. But I would still like to be able to say things about big O. I must also stress that some people define big O so that you're allowed to have negative functions. Now, for computer science, it doesn't make a whole lot of sense to have that, but you can do it. Like when you're counting stuff, it doesn't make a whole lot of sense. Okay. So, if there aren't any questions, by the way, keep in mind, feel free to hang out in the chat. Tell me how you're doing today. And of course, as per usual, let me know if you have any questions, okay, everybody? So as I previously discussed, there's different classes of functions, and we can organize these using big O notation. So for example, I can have, say for example, big O of n. Big O of n has, you can prove each one of these are actually in big O of n, or is. Each one of these, like n is big O of n. That's just a property that big O actually has. It's that I can say, whatever the function is, it inherits the big O property. It's what we call reflexive. So like n plus 1. So if I have a function, give it n, it spits out n plus 1. That's also big O of n. We proved previously actually that 2n minus 1 is also in big O of n. But there's actually other functions too. For example, as I mentioned, big O operates as an asymptotic upper bound, so there's other functions as well in here. And that's because of the definition of big O, right? It's because remember, it works like this. Remember, there exists the C and the N0 such that, so there exists, this backwards E means exists. There exists this positive real number and this positive integer such that whatever the function is, it has to be less than or equal to whatever the one that's part of the group here, okay? This complexity class. So sorry, this class of functions here, just to be a bit more precise. So notice here that the direction of the inequality. So for example, I can prove to you that 1 is big O of n. I can also prove to you that 100 or even 1,000 is big O of n. But it's not what we call asymptotically tight. We're going to have other asymptotic notation that exists that characterizes this, but we're not quite there yet. But there also do exist other functions too, such as 0 in our definition, because we allow our complexity function definition allows the function to take on the value of 0. It's out of convenience because sometimes we have algorithms and we're counting up the number of elements we're evaluating. Say, for example, I could give one example. If you ever heard of the algorithm called quicksort, sometimes the way you formulate what we call a recurrence relation in an analysis, sometimes people will allow it so that you can have it where there are no elements that are going to be examined. But the way that recurrence is formulated, it permits and serves as an upper bound on the running time. So the point I'm getting at is that when you're counting, it doesn't necessarily have to reflect exactly the operations. It might be that you're counting numbers of things associated with the running time of the algorithm. So that's why you might want to use that convenient definition I mentioned previously. But the point I'm getting at is that big O operates like an asymptotic upper bound. So I thought, hey, look, if we have a complexity function that is allowed to take on the value of 0, keep in mind this is a very convenient definition for us. It doesn't necessarily have to be that way, but we'll talk more about that at some point. But what I want to do is I want to see if I give you a function. So if I give you a function f and it spits out 0 always, so is that big O of 1? So does 0 belong to this set of complexity functions? Does it belong to big O of 1? So let's prove that using the definition of big O, if that's the case. So let's prove it together using the definition. Now remember, the definition says that there exist these two constants. Remember, this is a positive real number. This is a positive integer. We have to find these two constants such that for all n greater or equal to n0, let me just add that in right here. It has to be that this inequality is satisfied. So let's prove this together. And this is a really easy one, okay? You can easily pick up the pattern of this proof and use it in all sorts of different places. So to prove the claim, so I always like to make sure I start off with a little game plan so that the reader knows what we're doing. To prove the claim, we compute constants C, which is a positive real number. That's what the Blackboard R is with the plus. And N0, which is a positive integer. So that 0 is less than or equal to C times 1 for all n greater or equal to n0, right? So that's what the definition would be if we applied it. But notice that I want to get it so I pick up these two constants. So I got to find two constants. I want to pick them up. And I want to argue that these ones will work so that when I pick up and use the definition, so I'm just going to apply the definition of big O, it clears. So now this one's really easy, right? So let's simplify what we got right here. 0 is less than or equal to C times 1. So notice that C has to be a positive real number, right? So what does that mean then? Can it ever be that these are equal to each other? No, right? It has to be that there's a strict inequality here. But make this easier, because remember, all we have to do is present C and N0, right? But we have to check that they work by presenting an argument. So I'm going to select C is equal to 1. Let's go C is 1. So when I put C is equal to 1 in here, notice that this becomes just 1 times 1, which is 1. Then 0 is less than 1, right? Which is a subset of this statement, right? For all n greater or equal to 1, right? That's what it says. But that means that I'm satisfying the inequality always. So I'm just going to say by selecting, sorry, I was getting a little ahead of myself. By selecting n0 is equal to 1, we satisfy the definition of big O, and 0 has to be in big O of 1. And that concludes the proof. This one's a very easy one to prove, right? It's nothing too scary about this one. Remember the game plan. You find C, you find N0. It doesn't matter what order you do this. The recommendation I have for you when it comes to proving claims like this is you pick one of the constants, then you try to check the other one. So by formulating or deriving it. Sometimes it'll be a case where you can just choose both of them and then you check them, or you derive something by doing some algebra on the inequality, presuming the given domain of the numbers that we're working with, and then you get C and N0 at the end. There's several ways you can go about it. This is just one fairly standard way. But yeah, no, so now we know that 0 is in big O of 1. Pretty interesting stuff, right? So that brings me to an interesting question. So this is more of an academic question. That's the easiest way I can describe this question to you. It's more of an academic question because this, so now that I've told you what the definition of big O is, I've told you what we're considering complexity functions for our discussion. Remember, they could be, it's where the function takes in as input positive integer starting at 1, 2, 3. But you're also allowed, if you need more convenience, you can always make it so it starts at 0. But the output always is non-negative, meaning it's going to be negative. Sorry, no, it's always going to be 0, right? That's what non-negative means. It's not going to be negative. It means that it's going to be allowed to be 0 or greater. It can be fractional numbers. That's the whole point. It's allowed to be a real number. Now, in a lot of algorithm analysis, you don't need to go that far. Usually, just having a positive integer that gets outputted from the function is sufficient. That's typical for algorithm analysis. But from a lot of the models at play, very often you'll have it where the constants themselves appear in the running time, depending on the analysis. But that's a whole other side. So now, I'm going to ask you an interesting question as a consequence of this. Is big O of 0 equal to big O of 1? Now, I mean this in the most literal sense. This is an actual equal sign. So what I'm saying is, if I gave you big O of 0 and I give you big O of 1, are they actually the same? So are these the same? So what do I mean by that? So let's take the idea we have over here. So the first thing I need to show you is, remember that 0, and I must stress, you can take and pick up that proof that we just did over there. You can easily adapt it to show that 0 is in big O of 0. So you can do that. It's totally, if you use our definition, you're allowed to do this. But the question is, if I check what 1 is, so if I look for the function that outputs 1, is it inside of here or is it outside of there? That's the question we're going to address now. Like I said, it's a fairly academic question. So let's get into this. So the first thing is how do you know this? So remember that you think of these as buckets. So what my claim is what we're going to see here is whether 1 is in this bucket or there's another bucket out here that it doesn't, that it's sitting in. Because remember, that's how we talked about big O. It's going to be where the asymptotic orders of them nest into each other like that for the most part. So for what we're talking about. So, but we don't even need to go that far. We don't know whether it is going to be that these are in the same bucket or that these belong to two different buckets. But you're going to see that it's going to be more that it relates more like this. Because remember, what we established earlier is that 0 is big O of 1. And this is 1 right here, right? So naturally, a question is there a function that is not in here that's in here? So let's pick the easiest thing I can think of. So what I'm thinking, maybe we'll consider the function. We'll consider a function for which it outputs 1 always. It's just a constant function. So you might ask, Dan, how do we know? Like first, how do we prove that a function isn't big O of another function? So do you remember our definition? Remember our definition says that there exists a positive real constant c, a positive integer n0, such that this inequality holds for all n greater or equal to n0. Remember, in the game plan that we had, we would, what did we do? We find c and n0, and then we check to make sure that that works always, but we need to have an argument to do that. But, well, how does it work if I wanted to show you that you can't do this? What we would call the logical negation of this statement. So you can think of this like a game. So in that game, I have to pick up a c and an n0, and I have to show them to you and see if they work, right? Well, if somebody wanted to refute your claim, what would they do? Well, what would they do? Like to say that, oh, this function is not big O of that. What would they need to do? Well, think about it. If these two exist, these pairs of constants exist, and I can check it, we're good. So if I want to say that that f is not big O, then what does that mean? It means that you cannot find any pairs like this. So let me phrase this a little bit more carefully for you. So f is not big O of g if and only if for all c, remember it's a positive integer, this stuff doesn't change, right? These are just what I'm working with. And n0, which is a positive integer. So let's think about this carefully. So remember, it has to be that no matter which pairs I pick, do you remember when I first introduced big O to you, I plotted out two functions. I told you that there was eventually a point for which one of the functions dominated the other one. So how would I pop a hole in that bubble? So how would I show somebody that that doesn't work? Well, here's the thing. If I were to presume that if I picked up from an arbitrary bucket, suppose that there's a bucket of C's and N0s I could pick out, and I put them together. If somebody tells me those work, how can I show that I can refute that? Well, it's really not that bad. Well, remember, the whole thing was that one of the functions dominates the other by some constant multiple after some point n0. So all I have to do is show that if you give me that n0 and you give me that constant c, that I can find a value of n that happens after that, where that domination doesn't happen anymore, where the one function no longer dominates. At one point, any one point will suffice. So the game plan's a little different here, just a little. So if and only if for all c and n0, there exists n, which has to be greater or equal to n0, so this is some positive integer that is greater or equal to n0, such that what? So what did it mean to make it so that one of the functions goes a little higher than the other one by that constant multiple? It means that the inequality is false, right? It got refuted for that value of n. So this is what we would call the negation of the big O definition. So this is one standard way you can prove that a function is not big O of another function. So this is one way. Another way you could reformulate this is by using what we call proof by contradiction. There's other ways too, but we're going to use this one for this little exercise we're going to play around with. So we're going to consider this function here. So my claim is that 1 is not big O of 0. If that's the case, then it has to be the case that 1's sitting outside of big O of 0. So let's prove this together. So now that we have a logical framework for how we can go about this together, let's see what we can do. Now remember, now the game plan has changed. Now somebody's going to give me, as an adversary, they're going to give me C and N0. They're going to challenge me. They're going to say, hey, look, I got C and N0. What's my job? I have to give you a value of N such that it satisfies this property. That's the game plan. So I have to find N. So I don't have choice over C and N0 anymore. Somebody else does. But my argument has to work regardless of what C and N0 are. So you're going to see that the way this argument's going to work is that I'm going to have to be careful when it comes to this. So let C and N0 be arbitrarily chosen and fixed. So now remember the game plan? We're going to just say what the game plan is. So we find N greater or equal to N0 so that this is going to be one of those proofs where as soon as you write it out, it's just like, oh yeah, that's kind of easy. so that 1 is greater than C times 0. So here we go. Well, what's C times 0, everybody? It's 0, right? So let's write that. Well, C times 0 is equal to 0. So 1 is greater than 0 regardless of C and N0, right? It doesn't matter what C and N0 are. The point is now I have to pick N0. Sorry, pick N. Remember, you don't want to get those two mixed up. You want to pick N that's greater or equal to N0. So I'm just going to pick N0 to be, sorry, I'm going to pick N. I want to walk you through this thinking process, okay? So I need N to be greater or equal to N0. So what can I pick for N? I'm just going to pick N0. So I'm sort of trying to give you a little bit of a hint here or there. So choose N is equal to N0. And the inequality is satisfied. Now I'm going to pick up my negation of the big O definition and just invoke that. Therefore, by the definition of big O's negation, or what I would personally write if I was not doing this right now on the board, I would say by the negation of the definition of big O. So by the definition of big O's negation, 1 is not big O of 0. So the answer to this question is no. They're not the same sets of complexity functions. What it says is that 1 is sitting outside of big O of 0. And now, you might ask, Dan, why would we care about that? Well, this also gives you an indication that 0 is a little different than just any constant, right? It's just a little different, because what you can do is you can actually pick up and prove using the definition of the big O that, say, for example, big O of 1 is equal to big O of 2. Likewise, you can prove that if I give you two positive real constants, I can show you that big O of C1 is equal to big O of C2. Likewise, this simply means that I can compare, I can say, hey, look, any constant function, that long as it ain't 0, I can say that this set is equal to this set. This is equal to any constant d. So this d is greater than 0 is a constant. All of these sets of complexity functions are exactly the same one. So when somebody asks you, so a very common question that does come up is when people first see big O of 1. They say, why is it 1 as opposed to like big O of like 5 or something? It's because all of these are the exact same set, all of these. So it's easy enough to just call it big O of 1. That's a nice elegant way of classifying it. So if we're ever talking in terms of big O about, say if we're talking about a running time that takes constant time, normally it's expressed with big O of 1. If it's specifically constant, then you could say something else too. But the point I'm getting at is that big O of 0 is a little different. That's the main message here. So that's why it's one of these edge cases you have to be careful about. So you can say that 0 is big O of 1, but actually you can't say that they're equal. What you can say is that big O of 0 is a subset. So a fancy way of writing this is using this kind of rounded inequality here. Say, you can say that big O of 0 is a subset of big O of 1. Pretty interesting stuff, right? So are there any questions? Any questions at all? Any questions at all? I'm just going to get some water here. But yeah, no. So mostly today's lesson, I'm going to talk about some more examples. So what we're going to actually be moving into next once I get the boards erased here. So we're going to talk about big omega and big theta. And I'll show you a couple of examples. They aren't going to be like these ones. They're going to be a little bit more involved. Just a little bit more. But enough that you can play around with it a little bit. So after that, so what my plan is after that, we're going to talk about little o notation, and we're going to prove some claims using little o, using its definition. In fact, there's two ways you can write down the little o definition, at least two. There's another one as well, but I'm going to keep it to these two definitions because I think they're rather easy to play around with. At least sorry, I'm getting really excited here. Such that you can actually pick them up, and they're fairly easy to work with in a way that's very similar to what we just did over here, for example. So by the end of this, we're going to play with little o, and then we're going to ultimately get to the question if there's any algorithms that run in a specific running time. Because, like I mentioned, this is a weird case. Like, if you're doing algorithm analysis, you're never going to run into this case. It's a strange case. It has weird special cases around it when it comes to this. So, for example, big O of 0 is actually not the exact same set as big O of 1. That's why almost always, if ever somebody told you, hey, look, I have 0, they're almost never going to talk about big O of 0. It just doesn't really do a whole lot for us. They'll just say, okay, I'm just going to secede it to being big O of 1. But my only warning about that is that, like I said, it's a special case where this set is not the same as that set. So big O of 1 is out here. Big O of 0 would be contained within it. They're not the exact same set. So you have to be a bit careful about that little detail. But this is more of a fun edge case. At least I think it's pretty neat. It's something that isn't in a whole lot of books. So I thought I would talk a little bit about it here today. But also it's an excuse for me to give you more examples proving big O claims, which those are always helpful. I know that there's lots of space, especially like computer science students, or if you're interested in computer science, very often you have to get your hands dirty at some point with big O notation. So I want to make sure I do some examples here with you so that way you got even more examples. So let's head over here. But yeah, that's pretty much the game plan, unless anybody has any questions, because I'm happy to answer any other questions that people have. And keep in mind, it doesn't have to be about big O notation. You can talk about anything else, like games or whatever it is. It could also be like another big O problem or any specifics about some of these things. I can't guarantee I can answer anything on the fly, obviously. I'll just simply say I don't know, or I'll try to give you some guidance on where you can find it. But most certainly, we can get in a pretty good place with this. So anyways, let's talk next about a little bit more here. So let's all right, I'm getting really excited. Let's talk a little bit about this. So we got this. I just want to see where we're at here. So anyways, what we're going to do next is we're now going to talk about two more asymptotic notations. They're going to be helpful for us when we get to little o, okay? So let's talk about that. So next we're going to talk about another asymptotic notation called big omega. So big O is an asymptotic upper bound. This is the intuition, is an asymptotic upper bound. Big omega is going to be an asymptotic lower bound. So you're going to see that their definitions are going to be eerily similar. Likewise, that means that the strategies you would use for proving claims around big O it'll mirror in some ways for big omega. So we're going to let f and g be complexity functions. So we'll write that f is big omega of g. Big omega of g if and only if, so just as a reminder. So if and only if. So what this means is that if I say that f is big omega of g, whatever follows after this has to be true. And if this is not true, if f is not big omega of g, then whatever comes after this also has to be false. If and only if there exists constants. There exist constants. C, which is going to be a positive real constant, and n0, and n0, which is going to be a positive integer, so that for all n greater or equal to n0, it has to be that f of n is greater than or equal to c times g of n. Does anything in this just sort of stick out to you like a sore thumb about this versus the big O definition? So this is the definition of big omega. So if I say f is big omega of g, it has to satisfy this condition. So this should remind you a lot of the big O notation definition. So our big O definition. So it has two constants the exact same way we had them before. So the game plan has not changed in that regard. So your goal is to find the two constants, c and n0, but the inequality has changed. Do you see? The only thing that's changed here is I changed the less than or equals to a greater than or equal. That's why I'm saying it's an asymptotic lower bound as opposed to an asymptotic upper bound. So this is the definition of big omega. I think it's a good idea we consider an example. So we're going to show that log base 2 of n plus 2 is big omega of log base 2 of n squared. So this one's going to be a little fun because I'm going to use some properties of logarithms. So remember, I usually like to say the game plan so the reader knows what exactly we're up to. And remember, we're going to find the two constants. We're going to have to make sure we come up with an argument that guarantees that it's going to work for these two constants. And then I'm going to invoke the definition of big omega, just like I did for big O, to complete the proof. That's at least one way you can go about this. So we find constants. We find constants C, which is a positive real number, and N0, which is going to be a positive integer, such that log base 2 of n plus 2 is less than or equal, no, not less than or equal, right? Remember, that's what the big O one is. Big omega is greater than or equal to C times log base 2 of n squared. N squared is all together, by the way, for the argument for or input for the logarithmic function there. And this has to be true for all n greater or equal to n0. So here we go. So now we've stated what we're going to do, but now we got to pick a constant. So we got to think very carefully about this. So I deliberately picked this example to try to get you thinking a little bit, I wouldn't use the word in reverse, but most certainly something along the lines that I would like to engineer a constant. So sometimes when you're working on these kind of claims, there's a lot of standard techniques, but I thought I would give you a little bit of something that requires us to chew on a little bit. So I have an idea. I got an idea here. If I wanted to make it so that the left-hand side is greater or equal to the right-hand side, what I would like to do is pick the constant such that this looks like a term that looks like a logarithmic term like the one on the left-hand side. So I have log base 2 of n. I would like something that looks like log base 2 of n on this side, because I have plus 2 on this side, so I'd make it a little bit bigger if I need it to be. So here's a suggestion I have. Here's a suggestion. Is we can use a property here to help us. So we're going to use this one called the power rule or power law of logarithms. So here's a suggestion I have for this. So what we're going to do is we're going to use this property. This property says, hey, look, if I had something like this. So if I have log base 2 of n squared like this, or this could be any exponent here, what I can do is I can drag that out front, and it now becomes a multiplicative term. So this is actually equal to 2 times log base 2 of n. So the minute you observe this fact, so this is using the power rule of logarithms or power law. So the minute you observe that, what we really have on this side is c times 2 times log base 2 of n. Do you see a way I can just make it so it looks like log base 2 of n on the right-hand side? Any ideas? Well, yeah, well, let's think about it. So if I have a 2 right here, 2 times what is equal to 1? So what's 2 times what is equal to 1? 2 times what is equal to 1? So I could just make it so it's just log base 2 of n. Well, 1/2. I just take its reciprocal. So 2 times 1/2, these two cancel, you get 1, right? So that's what I'm going to pick as the constant. So I'm going to pick c is equal to 1/2. Then we're going to find n0. Then we find n0 so that for all n greater or equal to n0, log base 2 of n plus 2 is greater or equal to 1/2 times log base 2 of n squared, right? That's what it says. So now let's pull out our observation that we got over there using the power rule of logarithms. So that's what I'm going to say. Observe. So observe by the power rule of logarithms that 1/2 log base 2 of n squared is equal to 1/2 times 2 times log base 2 of n, which is equal to log base 2 of n. So now that I have that information at my disposal, let's do this now. So notice for all n greater or equal to 1, that log base 2 of n plus 2 is greater or equal to log base 2 of n. So choose n0 is equal to 1, right? Because the left-hand side now is, in fact, it's strictly bigger than the right-hand side. So I can just pick n0 to be 1. I must stress that n0 doesn't have to be 1. It could be, the strategies I tend to pick tend to make it so I pick C appropriately, so n0 is pretty easy to pick off. It doesn't always have to be like that. So now that I have C and n0, now I can say therefore, by the definition of big omega, log base 2 of n plus 2 is big omega of log base 2 of n squared. And that completes the proof. So that's my box at the end here. It sort of melted. It's actually, Miss Kitty sort of climbed on the box and sort of dented it with her weight. So just as a remark, this actually is an interesting case here because it actually shows you that when you have a logarithmic term like that, the power law or power rule of logarithms here, actually, it allows you to pull this down and it ends up just being a multiplicative term. So very often when you have proofs that involve logarithms like that, you'll find that this property tends to be very helpful. So at least especially when it comes to big omega or big O claims, you'll find very often this is the case. So that's big omega, everybody. So any questions about big omega? Any questions at all? Don't be shy. So as mentioned before, big omega is an asymptotic lower bound. So very often big omega gets used when you talk about requiring at least a certain amount of work, or at least a number of steps, as opposed to it being at most. So when somebody uses the phrase like they use big O, they're usually saying at most it's this much. When you talk about big omega, you're saying at least this much. It's a very common lexicon when it comes to big omega. So let's proceed here. So now that we've seen big omega, we're going to see another one. So this one actually is going to be the one I alluded to earlier about having this idea of asymptotically tight. So one thing I want to make a remark about is that, actually I'll say it when we get actually talking about the definitions. Let me get the definition up and then we'll play around with this, okay? Just make sure I got my example on both sides. Okay, good. Just want to make sure. Okay. So now we're going to talk about another asymptotic notation. So previously we've talked about big O, which is an asymptotic upper bound. Then we've talked about big omega, which is an asymptotic lower bound. So now we want to have a notation that represents asymptotically tight, meaning that it matches the exact order of whatever is specified for that complexity function, at least on asymptotic terms. So we're going to talk about big theta. And the way I like to remember that this is the one that is for asymptotically tight is it looks kind of like a big O, but it has the theta, because it's a theta symbol, like it's just theta. But the thing is, it looks like big O, but it has a line through it, so just a straight line. It's almost like it's tight, you know, it's on the same order. So very often when you talk to someone, it says, if I give you two complexity functions, f and g, and they say f is of order g, they usually mean this. They usually mean this. So for example, if you were dealing in big O terms, which I'll show you what I mean in a moment. Let me just get to the definition. So suppose I have two complexity functions f and g. We would say that f is big theta of g if and only f. If and only f. So remember, everything that comes just before the if and only f, this is true, then whatever comes after has to be true. If that's false, whatever's here has to be false. They're equivalent. If and only if f is big O of g and f is big omega of g. That's it. So my definition of big omega here that we've presented here for us. So our definition, this one is actually a combination of two definitions. So if you understand what big O is, and you understand what big omega is, you understand what big theta is. So let me give you an example just quickly before we get into like trying to use this definition for trying to prove a claim, is why you might consider big theta. Now suppose that I gave you a function that I say this represents the number of operations that occur in an algorithm in the worst case. Say for example, so let me just give you an example of usage here. So say if I give you a complexity function, it looks like this. Like 2n plus 5n cubed plus 2. Say if I count up all those operations in my algorithm in the worst case, I derive this guy right here for f. What would you say if I wanted to come up with the most asymptotically tight big O here? So a tip I can give you when it comes to big O notation is that you can drop these multiplicative constants and the additive ones, and then you look for the highest degree polynomial, because we have a constant number of terms. So if it isn't in that form, I recommend you do some more algebra playing around with it. So what you can do is you can show that this right here, this is big O of n cubed. So you can show that that's big O of n cubed. But what's also true mathematically speaking, there's that M word again, the mustard mayonnaise, making a good sandwich here. You can also say that this is also big O of n to the 99. This is also true. It's not very accurate of a statement about the running time of that algorithm, but it is a true statement. So when you pick up big theta is, as I suggest, asymptotically tight, meaning that the asymptotic lower bound from big omega and the asymptotic upper bound from big O, they're both satisfied. So there's going to be some sufficient point for n0. In this case, there's going to be now two constants, and there's going to be this case where now you're going to show that they're actually matching the same asymptotic order. So what you can say is that this is big theta of n cubed, but you cannot say that this is big theta of n to the 99. This is not true. It is not big theta of n to the 99. Likewise, if I were to give you an algorithm, say like binary search. Binary search runs in big O of log n time. Right? That's what you very often hear about binary search. It's also true because if you actually look at its complexity function, you can also establish that it is big theta of log n time. But you can technically, like I just said here, you can also say that binary search runs in big O of n log n time if you wanted to. You can say that. That's actually not incorrect. If you actually are picking up the definition, you use it. That is not a false statement. It's an inaccurate statement though. So this is actually true, just like that's also true. But the thing is, this is not tight, right? This is not asymptotically tight. So very often when you actually analyze the running time of an algorithm, very often you try to derive a complexity function, you analyze it so that you can obtain a tight asymptotic result. So you're normally, when you analyze algorithms with big O, you're almost always actually trying to achieve a big theta bound like this. So you're actually trying to obtain a big theta result, just Nobody's told you this up to this point. Just the other reason why that you haven't is probably because you haven't seen big omega. But if you ever are unsure, just pick up the definition for big omega and you can establish it after that, okay? So this is how you could use big theta. It's meant for if you're trying to say, yeah, it's actually just, it's this asymptotic order. So it's asymptotically tight. So it's not asymptotic lower bound, upper bound. It is both of them. It's not one or the other. It is both of them. So this is asymptotically tight. So this is the kind of thing you desire when you use big O notation in the first place. So now that we've talked about that, we have a definition for big theta. Let's do an example. Now, as I've suggested with our definition, it's really that if I wanted to prove a big theta claim, it's that I need to establish both of these things together. So these both have to be true. So if I'm actually studying and trying to show, hey, look, is this function, remember, this is a statement about functions, right? So I want to establish that f is big O and f is big omega of the other function. What does that mean? I can either prove those claims separately, but show that both of them are true, or I can attempt to take this definition and I can just sort of expand it so that I do it at the same time. So I'm going to try proving them together at the same time, but I advise that you take and break it into two parts to convince yourself that I've done the same thing. So here, let's do an example. Let's prove that 3n cubed plus 5 is big theta of n cubed. So what I'm going to do is, just to make this easier for myself, is I'm just going to try to identify one integer constant, and I'm going to have two positive real constants. If you want to have two separate integer constants, that's okay. I'm just picking the largest of the two values that would be your integer constants in this example. So just be aware of that little detail. So proof. We find constants C1, C2, which are going to be positive real constants. And we're going to find an n0, which is going to be a positive integer. Just as a remark, I'm just going to take so I'm taking the max of two integer constants. So you would have, for example, an n1 and an n2 to match up with the c1 and c2, okay? But that's not, this is just a remark. And n0 such that for all n greater or equal to n0, it has to be that c1 times n cubed is less than or equal, remember this is the big O part of the definition, is less than or equal, is it the big O or big omega? Well, let's write this out. And let's see what happens. So this is F right here. That's G, right? So maybe you have to be a bit careful here. Yeah, so if you look carefully at this, and I misspoke earlier because I want you to think about this. That's the whole point. So notice here that if you actually take this and you rewrite this the other way around, you'll notice that this is saying 3n cubed plus 5 is greater or equal to n cubed times c1, right? That's the big omega part of the definition. This right here is the big O part of the definition. So I've just chained them together as one longer set of inequalities. So again, like I've said previously, you can always try proving this separately. If this looks a little too complex, just take it apart, just pick up the definitions of each one separately, and just do it that way. So you might look at this and pick up one of the strategies that we've done previously. So for example, notice that I have something that's like 3n cubed plus a 5 if I can make something that looks like something in terms of n cubes that looks like this, but definitely will be larger than this, or matches it for all n greater or equal to 1, then we're okay, right? So I would like to do something on this side that matches that. Likewise, I would also like to get a nice lower bound on 3n cubed plus 5 by trying to get something that looks like n cubed, but it doesn't necessarily match the total size of this. And keep in mind, I could try to do that if I wanted to, but I would like to get a lower bound on it, as opposed to an upper bound like I was over on the right-hand side, or the rightmost inequality, to be a bit more precise. So what I'm going to do is I'm going to use my lookalike approach. We're going to pick C1 to be 3 and C2 to be 8. Now remember, the game plan is to find these constants, right? And we have to then show that they actually are correct. They work. We don't have to show all of them. We just need these constants to work. So I'm going to pick 3 and 8 because 3n cubed is less or equal to 3n cubed plus 5. It's just the same thing as this first term, and this has a little extra, right? That's okay. 8n cubed would be like, if I had 3n cubed, that would take away 3 from the 8, which would be leaving me with 5n cubed. And for all n greater or equal to 1, 5 would be less or equal to 5n cubed, right? That's sort of the mentality I'm coming in at this with. So pick those constants. Then we find n0 so that for all n greater or equal to n0, it has to be that 3n cubed is less than or equal to 3n cubed plus 5, but this also has to be less than or equal to 8n cubed. So we're going to take it in chunks just like I did before. So we're going to look at this part, and we're going to look at that part. If we can do that, then we're okay. So first, on the leftmost inequality, notice that 3n cubed is less than or equal to 3n cubed plus 5 for all n greater or equal to 1, right? I think this statement is easy enough for you to see directly, right? Because there's 3n cubed and then there's a 3n cubed here plus a little extra bit. Nothing scary about that. Second, on the rightmost inequality, on the rightmost inequality, 3n cubed plus 5 is less than or equal to 3n cubed plus 5n cubed, which is equal to 8n cubed for all n greater or equal to 1, and we're going to use our bucketing argument that we had before. So watch this. As 3n cubed is less than or equal to 3n cubed for all n greater or equal to 1, and 5 is less than or equal to 3. Sorry, 5 is less than or equal to 5. I was about to say 3, but it's actually 5. 5 is less than or equal to 5n cubed for all n greater or equal to 1. So now that I've shown you that I have 1 for the leftmost inequality, I have 1 for the rightmost inequality. So it means that if I take the largest of those values, which I must stress that if I wanted to have an n1 and an n2 instead of just a single constant like that, I would take the maximum of those two things. So in this case, I'm just going to choose n0 to be 1. Therefore, by the definition of Big-Theta, 3n cubed, that n's looking a little sad. Let me fix it up. 3n cubed plus 5 is big theta of n cubed. And that completes the proof. So the box just indicates the end of the proof. But yeah, so now that we have a family of different asymptotic notations, now we actually have a way of saying, okay, these are all of the linear functions. We have all the quadratic ones. We have the cubics. We have the constant functions. But we have to be a bit careful when we say that kind of stuff because when we talk about big theta now is a statement about O and omega, not just O. But yeah, that's big theta. So now that we've seen big O, we've seen big omega, we've seen big theta, the next guy we're going to be going for is little o. Little o, I know. You might say, oh, little o, that sounds so cute. Little o is arguably the one that I wanted to work my way up to because I wanted to be a bit careful about this. So little o, I find students tend to have a tricky time with it unless they are introduced to it only in a very specific narrow context. So I want to show you how you can pick up the definition and use it now that you are aware of these other asymptotic notations. So next, what I was thinking about doing is we're going to give the I'm actually going to give you two equivalent definitions for little o. They both use the same strategies, just they're recast in different ways. So I'll carefully go through those nuances with a couple of examples. Then what we'll do after that is we'll ultimately answer the question about, first, are there functions that have a certain form that are very small? And at first it sounds like a very silly question, but I'll have some discussion about it with you. Then also I'll answer the question of, are there algorithms that run in a specific time that is very small, so small that it approaches 0? So we're going to answer that question as well. And you're going to find that it's going to be an interesting sort of conceptual thought in your head. It's not a very, I would argue it's not a very interesting thing. It's just a very interesting thought experiment. But from a practical ground, you'll say, okay, that's why we don't do that. And that's the whole point that I'm getting at. So hopefully I make my point pretty clear. So let me just erase the board and then we'll get into our next examples and talk about little o notation. So if you have any questions, please don't hesitate to stop me. I've gone mad with power. I'm just joking. But no, if you're enjoying the content, make sure you tell your friends to come on out. I provide lots and lots of resources for computer science learning. And in particular, we spend a lot of time here on the delicacies of a lot of these things that I would argue are some of the trickier stuff that you learn in computer science classes. So that if you wanted to pick up and learn, say at a university, or say you want to pick up the stuff regardless and just want to learn the computer science, you're well equipped for learning the fundamentals of this stuff. So whether it's for your own interest or it's to enhance your own learning, that's what we're all about here. It's that and having fun. We're always about delivering a smile here. Okay. So next, what we're going to do is we're going to take a look at little o notation. So up to this point, we've talked about big O notation, big omega notation, and we've talked about big theta notation. We've seen some examples. I'm now going to talk about little o, which is another asymptotic notation. So let's define this together. So it's written usually with a lowercase o, not to be used with a capital O or a 0. So we say f, so if I give you two complexity functions, f and g, we say f is little o of g, if and only if So I must stress that whatever's here, if this is true, whatever's going to follow after the if and only if will also be true. If this is false, then whatever comes after the if and only if also has to be false. If and only if f is big O of g, and f is not big theta of g. So you might be looking at this definition. So let me just reiterate. So f is big O, sorry, f is little o of g, if and only if f is big O of g, and f is not big theta of g. So just to be clear what that means. So you already know that big theta is an asymptotically tight notation, right? Big O is an asymptotic upper bound. So if I want to use an analogy to explain this to you, if you know that big O is an asymptotic upper bound, you can think of that in terms of the inequalities. You find a C, you find an N0, and you show that F is less than or equal to C times G of N, correct? So this operates like, well, I like to think of it like less than or equals in terms of asymptotic growth of order. So it's like, so if I give you like a constant function versus a linear function, you could say the constant function is big O of the linear function, correct? But you can't do that with big theta, right? Big theta is an asymptotically tight notation, and it operates like an equal sign. So if it's saying that it's not big theta, that means it's not going to be asymptotically tight. Instead, that means, as a result, that it has to be strict. So what do I mean by this? So let me give you an idea what I mean. So the way little o notation gets used, is you can think of it as a, I like to call it and say it's a strict asymptotic upper bound. So for example, you can say that 1 is little o of n. You can also say something like log base 2 of n is little o of n. You can say, for example, that n is little o of n. But you, actually, can you say that? No, let's make it n squared. But if you were to say that n is little o of n, if you claim this, does that make any sense given this definition? No, not really, because sure, n is big O of n. That's not very hard to prove using the definition of big O. However, what's wrong with the n being a little o of n with this definition? Is that it's not allowed to be asymptotically tight to whatever's in the notation, right? So it can't be that, because remember, if I've established this, that means that what it's really saying is that it's not big omega of whatever that is. So it can't meet the asymptotic lower bound. It's strictly bounded from above when it comes to asymptotic orders here. So you can't say that n is little o of n. It's because it fails the second condition here. And one thing I need to mention, and it's just a sideline into this, is that when it says, since we know that f is big O of g, and that means that when I say f is not big theta of g, that really is me saying that f is not big omega of g. Do you see that? So this is going to come up now with our alternative definition for this. So this is an equivalent second definition. So I'm going to give you a second definition. There's a second definition. It's going to take the logic that's underlying this and put it together. So we can say that f is little o of g if and only if for every positive real constant, see, there exists an n0 that's a positive integer, such that f of n is less than, it's just strictly less than, c times g of n for all n greater or equal to n0. So this is the alternative definition. This should remind you of the big O definition. It just has some small tweaks to it. The first one is that you're not picking C anymore. C is arbitrary now. What you're picking in this definition is n0. So there's only one constant you have to worry about in this definition. It's just n0. You might ask, Dan, where did this come from? So, well, then the fact that inequality changed a little bit. So remember what I said. You have to prove that it's big O of the thing. So F is big O of G. So you can see that there's elements of that in here, right? So remember, if you were to show me this worked for every positive real constant, that definitely covers there being a positive real constant, right? So yes, that's in here. We find that there exists this positive integer. And it has to be that most certainly f of n is less than c times g of n for all of these, right? Like a lot of this seems similar. The inequality is sharp now as opposed to it being less than or equals. Now you might ask, okay, so why does it say for all c? Well, let's think back to when we're showing that something is not big O of another thing. Well, the argument is very similar for big omega. So what does this mean? If I know this is true, what it's really saying is that f is not big omega of g. So how would the game plan work in this? If it was big O, what would you do? Well, the direct negation of this statement would be that for all, so it has to be for all c and n0, right? It has to be for all of these. So c is a positive real number, n0 being a positive integer. There is n greater or equal to n0 so that, and remember in the big omega definition, it's that f of n is greater than or equal to c times g of n, correct? So if I negate that, that means that f of n has to be strictly bigger than c. Sorry, not strictly bigger. It is not strictly bigger, right? Remember, it's greater or equal for the original definition, so it means it flips like this. It's strictly less than c times g of n. So what you do is you take these two things, you lump them together, you get this. So you take the logic that entwines both of those conditions, you get this. That's where actually this comes from. So if you're wondering why this is the way it is, it's actually because you combine the underlying logic of these two statements. So if this is the case and this is the case, you get that. So you basically drop out the stuff that just doesn't work between both of them. So hopefully this gives you some appreciation for this definition instead of that one, but I'm going to show you how you might use these, okay? So I thought in the spirit of observing in our lecture, we're talking about small functions. I thought it would be a good idea we kind of try doing this with a fairly easy example. But do it in a way that is still in the theme of what we're talking about. So I thought the first thing we'll try throwing the little o notation at is, and we're going to use the second definition, and then I'll use the first one for another example, okay? So the first claim that we're going to try showing is that 0 is little o of 1. So that's what we're going to try proving first. So remember, the way we defined our complexity functions is we allow it to take on the value of 0. We'll have more discussion about this later. So anyways, we're going to try showing that 0 is little o of 1. So we're going to use that second definition. So remember, that one says that for every positive real constant, for any one that you pick, there's going to be, and keep in mind, you don't get the choice of it. It has to work for any one. There exists an n0 such that you get the sharp inequality here of f of n is strictly less than c times g of n. And it has to be true for all n greater or equal to n0. So here we go. So let us prove the claim using the second definition. I must stress that these definitions are equivalent to each other. There's nothing you can lose in between. It's just the way that you would go about proving it. The structure of it just changes a little bit. This sort of cuts out all of the other stuff, all the fluff. So, for any C, which is a positive real number, we find n0, which I must stress this is a positive integer, such that for all n greater or equal to n0, 0 is going to be less than or equal to c times 1. This is going to remind you of another example we did. And it's not a coincidence either. So, anyways. Well, what's the first thing you know about C? C is strictly bigger than 0, right? Well, C is strictly bigger than 0. So notice that regardless of n, so no matter what value n takes on in this function, the inequality is true. The inequality holds. So I'm just going to choose n0 to be 1. Therefore, so now I've done everything I need to do. Therefore, by the definition of little o, of little o, 0 is little o of 1. And that concludes the proof. So a couple of tips. So the first one is just remember the game plan. You don't have control over C. C is arbitrary. So you're going to imagine it like somebody gives you C in this claim. So I don't know what C is, but there's a big perk that we get out of having that, is that when I give you C, I'm allowed to pick N0 and I'm allowed to use C. So sometimes when you're proving claims involving little o, it'll be the case that when you pick N0, it might have a relationship with C. So if I give you a C, then I can show you how to get N0. So that's a tip I can give you about proving little o claims. So beyond that, you're going to find a lot of the strategies we've used in the past for big O will generally be helpful here. But the point is that we need to make sure we pick that constant big enough that will satisfy it in this case. So actually, I'm just staring at this a little bit. I noticed that actually I wrote less than or equals. This is sort of my mental memory going on here. So it should be that it's less than like this, right? I didn't have anybody to correct me, so I'm just gonna fix it there. So either way, our argument still works, right? That's what I was saying. It wasn't a coincidence. So hopefully this argument makes sense for everybody. So just remember, it's a strict inequality there. But yeah, so that's how we can prove 0 is big O of 1. Not big O of 1, it's little o of 1. Because we already, by the way, if you're curious, if you haven't tried or seen this, yeah, you can prove that 0 is big O of 1. So anyways, what we're going to do next is I'm going to now show you how you can show that something is not little o of another thing, okay? So now that we've seen that 0 is little o of 1, let's show that, that there actually are functions that aren't little o of a something. So you're going to find that the first definition that I gave you is actually going to be helpful when you want to accomplish this. So remember in the first definition, I'm just going to keep up these conditions here. So the next example we're going to do is actually going to be proving an is not claim. So as opposed to an is claim like we just did. So previously we've shown that 0 is little o of 1. I'm going to now show in our next example that a constant like 2022, I just thought because it's current year and all, that this is not little o of 1. We're going to try proving this. So the reason why I like to show at least a couple of ways you can define little o is that when you think of this simpler one where we have f is big O of g and f is not big theta of g, what does it mean for this not to be true? So remember, this means that both of these are satisfied. So what does it mean for this to be not true? So if I number these 1 and 2, so if I want to satisfy the little o definition, it has to be that it satisfies both 1 and 2. For it to be not true, what does it mean? It means that one of 1 or 2, so one of 1 or 2 fails. So it gives you a recipe for quickly proving that something is not little o of a something. So here we go. So what I'm going to do is I'm going to negate the definition. So negate the first definition that I gave you, but I'll just call it the definition because that was the first one I gave you. Then we can show at least one of 2022 is big O of 1 and 2022 is not big theta of 1 is false. Remember, that's our game plan. So this is our game plan here. So I have a question for you. Which one is the better strategy here? So which one of these should we tackle? Well, I can first tell you, and I want you to convince yourself of this, is that 2022 is in fact big O of 1. So this is actually a true statement. That's true. So which one is the culprit if this is what we're trying to prove up here? It's this one right here. So if you wanted to refute this claim, what would you do? So if you want to show that this is false, what are you actually trying to do? You're trying to show that 2022 is big theta of 1. That's what you do. So I'll say, it is true that 2022 is big O of 1. So to prove the claim, we show that 2022 is big theta of 1. But what part is missing? I already know that's true, right? And keep in mind, if you're not convinced by this, if you want to exhaust out this proof, I encourage you to do that. Do this part of the proof. So we show this. Since 2022 is big O of 1, what remains is to prove that 2022 is big omega of 1. So if we can prove that, then we're done. Does everybody see that? So that's all we got to do. Just gonna try a different marker. So now all I got to do is prove that 2022 is big omega of 1. we find constants. We find constants c, which c is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, I'm just going to switch my marker again. I keep switching markers. This one's starting to act a little funky, so I'm going to switch to a different marker. Let's try a different one. Such that for all n greater or equal to n0, it has to be the 2022 is greater or equal to c times 1. So this is surprisingly easy for us to approach if you understand what we just wrote down. So I picked those two constants such that 2022 is greater or equal to c times 1. What's a natural lower bound here? If I pick c is equal to 1, right, then I have 2022 is greater or equal to 2000, well, it's greater or equal to 1, right? That has to be true. If you really don't like that, you can always set c to be 2022, then they're equal to each other. But the point is there's a lot of flexibility for how you pick this constant. So I'm just going to pick c is equal to 1. Then 2022 is greater or equal to 1, which is true for all n greater or equal to 1. So select n0 is equal to 1. So now we got our two constants. We have something to check that. We have an argument for that. Therefore, so now we can put this all together now. Therefore, by the definition of big omega, 2022 is big omega of 1. And as a consequence of the argument we have above, and as a consequence, that says consequence over there, it sort of melted in the microwave a little bit. And as a consequence, what does that mean? It means 2022 is not little o of 1. And that completes the proof. So I thought I would give you some examples of how we can use little o in some basic examples. So if you thought that was kind of neat. So notice that little o, I find, is a little easier to manage if you understand that it's really comprised of these two parts. Is there any questions or anything? Don't be shy. Happy to answer any questions. I'm just going to grab a different marker because my markers are starting to act a little funky here. Because we're going to do a little bit of a... I would argue it's not that challenging, but most certainly it'll require a little bit more thought than these examples did. So I'm going to get us another marker here. So if you hear any strange noises, please don't dream about it, okay? Okay. Just want to get a couple more markers. But no, I hope you're having a wonderful day so far. We're actually just about approaching our main question of the lecture. But I want to show you something that is interesting. Because we've established that 0 is little o of 1. But that's not a very interesting result, right? Because it's 0. The whole intuition with this is that it's of an asymptotic order that is strictly less than the one I have inside of that notation, right? So 0, it's 0, right? It's not very interesting. What about something that actually has an n in it? So we're going to start. So naturally, you're going to find that a lot of the functions you're going to run into when it comes to little o are going to actually have a tendency, and this is actually how you would think about little o, especially when you think about it as little o of 1, it's going to eventually get to being something that is going to be strictly less than whatever is inside of that notation. So for example, if I'm talking about little o of 1, well, there's nothing else below little o of 1, all right? Sorry, big O of 1, it's just 0, all right? At least if we're talking about our common classes of complexity functions, right? So it's a constant function, then we have the 0. So if we're going to talk about anything that's little o of 1, as kind of the theme of today's lecture, it's going to be quite natural that we're going to run into things that are going to be sufficient. When they get sufficiently large for the input, it's not going to be something you can bound appropriately when it comes to a constant. So it's going to keep getting smaller. And remember, that comes to the same intuition we had before about our big omega, right? Remember, we wanted to show that it's that if it fails the Big-Theta definition, then it has to be that that it's not big omega, because it has to satisfy the big O definition. Man, this eraser's starting to get a little dirty. So let's get to our next example. So I want to address here and try to find another example of a function that is in little o of 1. Now previously we established that 0 is little o of 1, but it's sort of a contrived example, right? Because we've established earlier in a previous lesson that 0 is, like big O of 0 is actually a strict subset of, like it's a proper subset within big O of 1. It's a special case among constant functions. So I want to show you that there exist other functions, presuming you're allowed non-negative real valued functions. So here's a claim. I'm going to prove for you that 1 over n is little o of 1. So we're going to try proving this. So we're going to try proving this in two parts. So remember, we had our first definition and then our second definition. The second definition is where we take all the logic out of our first proof and we kind of slam them together in a logical conjunction. So we bring them together. It's them put together as an and. Sorry, I'm getting a little excited here. My point is that they slam together, kind of like a really epic Kool-Aid commercial. So remember that our definition was that we have, if I have f is little o of g, this means, this is no different than me saying that f is big O of g, and it has to be both this and that f is not big theta of g. But remember, as we talked previously, the whole thing is going to be set up where if that's the case, and we know that the definition of big theta is that it satisfies big O and big omega, then it has to fail for big omega. So this is actually me saying that f is not big omega of g for our proof. So just keep that in mind when we walk through this example, because it's going to be an important setup for how we're going to break this into cases. So I'm going to first show you that we can satisfy the big O part, and then I'm going to show you that you can satisfy this second part that says it's not big theta. If we can do that, then we've satisfied the little o claim that we need to prove. So proof, well, let us prove this in two parts. In two parts, I'll say two with the word. In two parts via the definition. So let's look at the first part. Let's first prove that 1 over n is big O of 1. So what do we have to do if we're trying to prove the big O claim? We need to find constant c, which is a positive real number, and n0, which is a positive integer, such that 1 over n is less than or equal to c times 1 for all n greater or equal to n0, correct? That's what we need to do. So let's write that out. We find constants. Constant c, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, 1 over n is less than or equal to c times 1. Okay. Now here's a beautiful part. Let's see what 1 over n actually looks like for different values of n, just to convince ourselves of the following thing, just in case you forgot how fractions work, because you never really know what happens in your day, okay? All you can have is the funniest of brain farts, and then suddenly you forget how fractions work. So anyways, well, 1 over 1, that's 1, right? This is equal to 1. The next term that would be in this would be 1 over 2, that's 1/2. The next one would be 1/3, next would be 1/4, and so on. Notice that all of these are less than or equal to 1. It never gets bigger than 1. It's always less than or equal to 1. So let's use that information. So notice that this on the right-hand side is going to be 1 if I let c be 1. So that's how I'm going to pick c. Pick c is equal to 1. Then observe that for all n greater or equal to 1, that 1 over n is less than or equal to 1. So choose n0 is equal to 1. Therefore, by the definition of big O, so now let's invoke the definition of big O. Therefore, by the definition of big O, 1 over n is big O of 1. That's the first part of the proof. So we got the first part. What's the second part? The second part is the proof that f is not a big theta of g, or in our case, that 1 over n is not big theta of 1. So remember, we've established this first part, which is actually a part of the big theta definition. So 1 over n is not big theta of 1. That's the second part of our proof. We showed in 1, so the first part, that 1 over n is big O of 1. So by the definition of big theta, so what does that mean by the definition of big theta? That means that it must be the other condition of big theta that went wrong. By the definition of big theta, it has to be that 1 over n is not big omega of 1. So now let's take the negation of the big omega definition using the same game we've seen in previous lessons. So remember, in big omega, if we try to prove a big omega claim, we have to find the two constants c and n0, similar to our big O claim that we had over here, except you would have it where the inequality is a greater than or equals as opposed to a less than or equals, right? So the question is very natural. When you flip it, make it a negation of that claim, then you're going to have arbitrary c and n0 given to you, and you have to show that you can always find that n such that f of n is strictly less than c times g of n, as opposed to greater than or equal. But you have to pick n big enough such that it's greater or equal to n0, right? So then, by the negation of the definition of big omega, for any C, it's a positive real number, and n0, that's a positive integer, we find n greater or equal to n0 so that 1 over n is strictly less than c times 1. So now what we need to do is we need to presume that we're given c and n0 that are arbitrarily fixed. So presume c and n0 are arbitrarily chosen and fixed. So we need to make sure we can satisfy this inequality no matter what c and n0 are. So remember, the whole game is that they give you c and n0, and you have to give me an n that always works. If assuming that they said, hey, look, 1 over n is actually big omega of 1. So they have to show you, they give you these two constants, you have to show how to refute it. So let's think about this. So next, let's try to find n. To find n, notice that. So this is usually the part of the proof where you try to do some clever thinking. So notice that it's 1 over n is less than c times 1, and c times 1 is just c, right? But also remember, c and n0 are both positive, right? They can't be 0. So what does that mean? That means that I can multiply both sides of this inequality by n, and then I can divide both sides of the inequality by c. To find n, notice that 1 over n is less than c if and only if. So I'm going to use this double arrow to indicate if and only if. So this is just done via the steps I just mentioned algebraically. Less or equal to 1 over c is less than n. So now that you can see that now I can get n on one of the sides of the inequality, now I just need to come up with a sufficient upper bound on 1 over c. And then I pick n to be appropriately large. And for any c greater than 0, so we have 1 over c. Okay, I'm going to try making something that's bigger than 1 over c. So one natural way I can start is I'm going to try to make it into something, because remember, I have to find n. And n is an integer, right? It's a positive integer that's greater than or equal to n0. So I can't just simply make it so it's c. C can potentially be a fractional number, for example. So 1 over c, what I'm going to do is I'm going to make it so that when you carry out 1 over c, you're going to round that up to the next highest integer if it has a fractional part. So what I'm going to do is I'm going to introduce the ceiling function. So 1 over c. Now if you've never seen the ceiling function before, it works like this. So if I give you, say, 2.5, you would write down 3. If I give you a 2 inside of the ceiling, it's a 2. If it's 2.01 with a ceiling around it, it's 3. It rounds up to the next integer. If there's a fractional part, the easy way to describe this is you always round up by default. If you have a fractional part like this, you're going to round up. This is in contrast to something called the floor function, where you take and scrap off the fractional part, and implicitly you're rounding down. So if you have an integer, you end up with the same integer. If you have a number with some fractional part on it, if it's a floor function, so this is the ceiling function, just to be clear. So this is the ceiling function, or ceiling. You always round up. So naturally, if I take 1 over c, and then the result of that I'm going to round up, I end up with either the same value or greater. then naturally I want to make this a little bit bigger. I want to make it a little bigger than this because remember, I need a strict inequality. That's what I'm required to get, is a strict inequality like I have here. I need to make sure whatever I get as a result of this is going to be strictly less than n for the sufficient, when I pick n. So it has to be that n is greater or equal to n0, and it has to be that this inequality actually holds for that particular value. So all I'm going to do is I'm just going to tack a 1 on, just to make it slightly bigger. So this is indeed an integer, but I must stress that this statement in itself doesn't require it to be an integer. I'm just saving myself a little time, because all I'm going to do now is I'm going to select n. And now remember that I need to pick n such that n is greater or equal to n0, and it has to satisfy that inequality over there. But what did I say here? I actually gave you a way to pick n, right? If I pick n to be this, then this inequality is going to get satisfied, no matter what c is, because c, it can be any value greater than 0, and this will be satisfied. So what I'm going to do is I'm going to use a max function. So I'm going to take the larger of these two values. So I need n to be greater than or equal to n0, so I'm going to say n0. That's one of the choices. Or it's going to be the ceiling of 1 over c plus 1. So whichever of these is the larger one, you pick that as n. That's the recipe. Therefore, by the negation of the definition of big omega, 1 over n is not big omega of 1. Now, since we have the two parts now we can say therefore, by the definition of little o, it has to be that 1 over n is little o of 1. And that completes the proof. So now we've established, presuming our definition of our complexity functions, that yes, there do exist other functions that are in little o of 1, such as 1 over n. Just a small typo in my notes. So anyways, are there any questions or anything like that? Don't be shy. Don't be shy. Happy to answer any questions. Yeah, so now we have a couple of functions that are in little o of 1. So I must stress, I have not talked about algorithms yet at this point. That's really what I'm going to focus on last, because now it all boils down to how we've considered our functions, right? Because we haven't talked about an algorithm. The whole idea is that we formalize and count operations, and it becomes one of these kinds of functions. But the thing is, maybe our definition doesn't necessarily reflect actually any one algorithm. So that's what we're going to focus on here finally. So like the last little bit here is that we're going to see that actually we have to be a bit careful about making presumptions about the nature of algorithms and their running times with respect to our complexity function definition. So sometimes when you talk to some people about the definition of a complexity or growth function, they will adapt it so that it's easy to work with, like the way we have it. Or they'll make it very strict, where it has to be that there's always an algorithm that will have a running time of that type. So keep in mind, to make ours have some meaning, you would have to have it where you allow some things that a lot of people would think is a little silly. So we're going to talk about that. So I'm just going to erase the board here. So we showed that 1 over n is little o of 1. And that makes sense if you actually think about it from a sequences standpoint, that if you take n and approach infinity, with 1 over n, you'd expect it looks like a 0, right? So you're not going to be able to bound it by some constant, hence why it doesn't satisfy the big omega definition. So just remember that the complexity function, that as we define it, is that we define it that way out of convenience. So it's easier for us to count things with being rather charitable. But I must stress that that still doesn't ultimately answer a question that we had, because we've established that there are functions, as we've defined them, that allow us to say that they belong to little o of 1. Such as 0 and 1 over n. So the final thing we're going to talk about here, this is kind of like the last thing I was hyping up, and it's actually going to be cute in the sense that it's not a very, I think it gives you an insight into thinking about complexity from an algorithmic standpoint, but it's also just more of an edge case. It's not, I would argue it's not terribly, it's not going to be mind-blowing, but most certainly the concept of it is a little bit different. Especially something that most people would just say, yeah, look, that's just a silly edge case. We would never consider that. And I really want you to appreciate this observation whenever you hear it from someone like me in the future. Like whether it be that you find it in a book or something like that, and why you wouldn't have functions that look like this for a corresponding algorithm. So let's talk about it now. So now what we're going to do is we're going to talk about a question. I think it's an interesting question. And I'm hoping it'll give you some appreciation for how we might consider a complexity function that measures the running time of an algorithm versus the question of having what we might call a complexity function, which is just a function, just to be very clear. And the question of those exist, they have relationships with asymptotic notation. What about algorithms? So here, I'm going to frame this in the following way. So are there algorithms that run in little o of 1 time? Not to be confused with big O of 1. Little o of 1. So before we get there, just want to remind you of just a concept about our asymptotic notations. Remember, these are sets of complexity functions. So as we define the complexity functions, they are allowed to take on as output a non-negative value. But it's a statement ultimately about functions. That's the point. So the set little o of f is empty. It's empty if it contains no functions. It's an empty set. So based on some of the things we've observed in the past, we know, based on our definition of a complexity function, the question is little o, is little o of 1 an empty set? So little o of 1 is not empty. It's not an empty set. It's not empty for our broader definition. Remember, I said out of convenience, we allow it to take on some values that maybe not necessarily one that we need, but it's just helpful for our broader definition of a complexity function. Why? Because we established that 0 and also functions like 1 over n, these are in little o of 1. So we proved these previously. So there's other ones as well, but those are just 2 examples. So what we're really asking when we say this, because there do exist functions that are in little o of 1. Just the question is, do these actually represent the running times of algorithms? That's really the question. So really, are there algorithms with complexity functions of this kind? That's really what we're asking. Is like, can we have an algorithm that runs in little o of 1? Does its running time is it something that takes the form of 1 over n? Is it allowed to take no operations at all? And that gets you out really in what we're talking about here. So remember, our definition of a complexity function, at least the one that we've been using for our discussion, is that if I give you a function f, it takes in a positive integer. It's also okay if we allow it to take on the input of 0, but it produces a non-negative real number. But here's the thing. Can an algorithm, so this is more of a broader question. It's something that is contestable, but most certainly is something that would be, if you were to ask your average computer scientist, like, does that make sense to have? Most of them would tell you no. Is it possible to have an algorithm that has no instructions or operations? Like, none. Like, there is nothing to it. Is there such a thing? Is it even called an algorithm if there is no instructions? Like, is that really a thing? So some people like to call this an algorithm with no operations or the empty program. So if we presume an algorithm must have at least one operation, and you can make a lot of arguments in favor of this. For example, many times when you start an algorithm, you have to have some way of telling the person to stop. So as in, for example, returning an answer, it may be the case that that you need some way of designating when the algorithm is finished. That's an easy way to argue that such a thing has to be the case. Naturally as well, just from a standard of describing what an algorithm is, if you have no instructions, is it actually an algorithm? That's sort of a fun question for you to think about. Is it an algorithm if it has literally no description? So that's another way you can think about this as well. So if we presume an algorithm must have at least one operation, then what does the complexity function look like? Then the complexity function f of the algorithm. So suppose you're doing worst case analysis just for the sake of this. But either way, we're just trying, say if we're just counting up how many there are at least in such a case. It doesn't really matter. It's just imagine you're just doing like an exact analysis, that there's at least one operation, right? As long as there's at least one, it doesn't matter which case you're talking about. I'm getting broader when I say these things. Of the algorithm f, we'll say satisfies the following: that f of n is greater or equal to c for some c greater than 0. Now, if we're counting discrete steps, so if you're counting how many operations or primitive or elementary operations are happening, if you treat each one as a single step, then c would be 1. But I'm just trying to keep it flexible here, just in case you're wanting to have it where we're counting, say, like CPU cycles or time and things like that. I'm trying to keep it as broad as I can. So if you have at least one operation and it takes at least C many operations to occur, then what does that mean? Well, most certainly it can't be less than 1, right? Sorry, it can't be 0, nor can it be what? It can't approach 0. That's where I'm going. There's not eventually a point where it hits 0. Or it approaches it. So it doesn't hit 0, it doesn't approach 0. It always has this constant amount that has to happen. Whether it be a half, if we want to think about it in that weird way. Typically you wouldn't. You think of these as discrete steps. So you think of, for example, let me give you an example. Like say if you're thinking about a model computation such as a Turing machine, you count the number of moves that occur. If you have at least one operation that must occur, or at least one move that must occur, that is one operation, or one move, right? And that's what would happen in a program that has at least one operation that must happen. So one step. So for example, you have a state and then transitions to a final state. Or it's going to be moving into a final state. Anyway, my point is that there's going to be at least, it's not going to be approaching 0. It's always going to be bounded by some constant, which will fail your little o of 1 definition. So I'll say f of n is greater or equal to c for some c greater or equal to c greater than 0 for all n greater or equal to 1. So if you make this presumption, no algorithm has a complexity function. That is little o of 1. So really this boils down to the following thing. Do you accept the existence of an empty program or an algorithm with no instructions? If you do, then the answer is sure. But in any setting that you're going to run into for typical analysis of algorithms, you will not. So my answer would be for this is that the answer is no. But most certainly it's up for debate if you want to accept if there's an empty program or not. So, that being said, I want to say thank you so much and have yourself a beautiful day. So let me just get some last bit of discussion here on one thing. I got one interesting point to bring up. So, you know how we talk about big O of 0 and little o of 1? So hopefully you thought this was kind of interesting, is that you can't have a running time that eventually approaches 0. That's what I'm getting at, is that there has to be at least one operation that occurs. You can't eradicate that one step of operation. But in that one step, it might take some C many operations, but the point is it's still a constant, right? You can't just simply eradicate that. And we've previously established that that in our previous discussions, we showed that if you give me a constant is not little o of 1. It is in fact big O of 1. In fact, the reason why it's not little o of 1 is because you can show that it's not big omega of 1. Because a constant won't get vanishingly smaller than small and approach 0. That's the point. But yeah, no. But yeah, the big point I'm getting at is that if you have so if you have at least one operation, it takes some constant many operations, whether it be a 1 or any one that's greater than 0, you can't, as we've shown previously, you can show that a constant is not little o of 1. But yeah, no. Are there any questions or anything of the sort? Hope you thought that was interesting. I thought I would show you some more examples with using big O, big omega, big theta, and also I gave a couple examples because I haven't previously given any examples for little o. I thought I would give you a few examples of using little o. Because I previously talked a little bit about it, but I'm not like used the definition and shown you it very intricately. And yes, we have some fun spam in the chat. Oh, but no. But other than that, we've seen a bunch of examples. That's it, pretty much everything I got. Are there any questions? Don't be shy to ask questions. It's rather quiet here today. Either way, hopefully you find this resource helpful. One thing I'll point out is that the notes from today's lecture will be available on Patreon at patreon.com/pagewizard. So I'll have those available there today, like a little later. Just got to fix a couple small typos I spotted. But yeah, other than that, they'll be available there. And of course, I don't see any questions, so I think it's a good place for me to stop. So I'm going to say thank you very much, everybody. And of course, if you enjoy this content, make sure you subscribe, tell your friends to come and hang on out. And of course, make sure you leave your day with a nice smile, okay? So other than that, I'll say thank you so much and have yourself a beautiful day. I'll see you later.